With the lecture of Professor Gogotsi, we will learn more about carbon nanotubes. Please let us welcome Gogotsi.
Good afternoon, everyone. I know that you're tired, you're exhausted, you're oversaturated with information after a day full of lectures here. So I will try to keep it relatively short, at least to stay on time. And last time I started my lecture with a brief introduction to research activities at Drexel. What I realized, I never showed to you any pictures of our university. And what you see here on screen is actually downtown Drexel University. The small building in the back is actually not that small one. This is the largest town hall in the United States. It's the City Hall of Philadelphia with William Penn statue on top of it here. But what it shows you that Drexel is located just at the edge of downtown, sharing campus with University of Pennsylvania in the area which is called University City. And my office is right in this building, in this corner, and this window is window of my lab. So this building is actually, and this picture is here, and the adjacent building, our Basson Research Enterprise building, where we have our Nanotechnology Institute. So the first floor has centralized research facilities, microscope spectrometers, including Raman spectrometers, which were used to produce much of the data I'm going to present today, and other instruments. And another floor contains labs here. Now, something else I promised to you last time. Several of you asked me about whether natural carbon nanotubes have been found, whether they occur in nature. And my answer was yes. In hydrothermal vents and hydrothermal graphite, there are carbon nanotubes. And if you were in the room, you might have seen a slideshow accompanied by music that one of my former PhD students, Svetlana Dimovsky, put together. And conical crystals you saw there were actually natural cones. These are relatives of nanotubes. In very similar samples, we also observed multiple carbon nanotubes. So they are possible in natural environment, and they have been found on the planet Earth here. Now, few more people asked me about carbon nanotubes and liquid crystals. There have been some work done in literature. I even got involved with one of my colleagues, Professor Adam Fontecchio, who is a liquid crystal guy. I'm not myself. I'll just show you a couple of slides to briefly tell you what we did. We added carbon nanotubes, straight multiple tubes, to liquid crystals, showing that when you rotate by applied field perpendicular to the sandwich here, carbon nanotubes can short circuit the electrodes, leading to the nematic to isotropic transition in the liquid crystal. And for this, you need to select just conducting carbon nanotubes with conductivity above a certain limit and length which is longer than 10 microns. This was the difference between the electrode. So what you will observe in this case, you initially will see this formation of black spots in the liquid crystals, which will then quickly expand, propagate until the whole area darkens. And on the way back, you nicely have a pretty regular transition here. So for example, if you damage the display, you can have a transition to isotropic state by using this nanotube containing liquid crystal. We also played with introduction of magnetic tubes into liquid crystal a little bit with a similar purpose, either to enhance switching, make it faster, or do insert other control. What you see here, it's not a liquid crystal, it's just a solution of I think isopropanol in this case. These tubes are magnetic tubes filled with superparamagnetic metal oxide particles, iron oxide. And when you apply magnetic field, they all align along the field. Moreover, there will be always some distances between the tube. You can calculate that elongated paramagnetic object will basically show some repulsion, and there will be optimum distance depending on the length and magnetic moment here. So, and what you see here, this is the same image, but we applied magnetic field in different directions, so all these tubes are standing normally to the surface now. It just shows to you how you can nicely control carbon nanotubes by using electric or magnetic field. So there are definitely applications for this type of, for example, arrangements in various type of gratings, and you can do a lot of neat things with those. But today, I'm not going to continue talking about carbon nanotubes conducting transparent films and other things here. I'm going to move to the topic of this lecture, spectroscopy of carbon nanotubes. And primarily, I will be talking about Raman spectroscopy. What you see here is a fairly common dispersive Raman spectrometer from Renishao. I talked to our Chinese colleagues yesterday who are expecting an instrument like that to come in the fall. We have 3 Renishao spectrometers at Drexel, and are expecting one more to arrive within a month or 2 that we will be using for biological applications. And for those of you who are specifically interested in Raman spectroscopy of carbon nanotubes and other carbon nanomaterials, I can recommend this special issue of Philosophic Transaction of Royal Society, published in 2004. It was edited by your colleagues, Flynn, Andrea Ferrari, John Robertson from Cambridge. And it contains very nice reviews, of course including one of our reviews on carbon nanomaterials, everything from diamond nanotubes. What it doesn't have covered, it doesn't have graphene, just because the graphene story broke in 2004, just at the time the journal was published here. But you will see plenty of references in my presentation. I won't talk just about Raman spectroscopy. I will also talk about fluorescence spectroscopy and really light spectroscopy a little bit at the end of my presentation, if I have time here. So, why does anyone care about the optical properties of carbon nanotubes? This is another question some of you asked me after my first lecture here. There are quite a few reasons for this. And one of those reasons is that if we understand optical properties of nanotube, we can get nice spectroscopic signature of nanotube structure, quality, and it means also properties of carbon nanotubes. So, for this, and I will talk later about this type of fluorescence spectroscopy, we need to understand optical properties of nanotubes. So we study absorption, emission, and of course the Raman spectroscopy, to lesser extent infrared spectroscopy, and I'll explain in a moment why here. But there are certainly also potentially spectroscopic and optoelectronic applications for carbon nanotubes, including, for example, gratings that I mentioned can be produced using magnetic tubes here. So, you can tune the band gap in nanotube, and this is useful for a variety of applications, as you understand. We have one-dimensional, pretty unique structures in carbon nanotubes, and we have a very, very large variety of materials that can be finely controlled here. Producing fluorescent agents, LEDs, detectors, nonlinear optical elements, and there are a lot of activities going on in the field, for example, at IBM with Fede Navouris being one of the leaders in the field here. And also, we can probe fundamental physics of the excited states and dynamics of excited states in nanotube here. Looking at the position and character of excited electronic states, mechanisms of light emission from carbon nanotubes, carrier, for example, electron-hole interactions, excitons in the troop and their consequences, effects of environment. And again, this can be used for practical application in sensing with carbon nanotubes. and we can study phonons and electron phonons interactions here. So there's quite a few reasons why there are numerous people in the community who work on optical properties of carbon nanotubes here. My talk will be focused on spectroscopy of carbon nanotubes because if we try to cover all of the subject, you would spend the rest of the day here in this room. And I see some people already yawning and definitely are tired already here. My understanding was that in this room there are several people who are experts in Raman spectroscopy. Can you raise your hands who know everything about Raman spectroscopy? Or Mariana knows definitely more than I do. Elena, I guess, too, and Sasha. And my understanding was also that quite a few of you have used Raman spectroscopy or planning to use Raman spectroscopy in research, whether those are lipid crystals, inorganic materials, or others. You also had a lecture on cars, which is an exotic Raman spectroscopy or Raman imaging technique, which is used anti-stops Raman coherent and stopped Raman scattering here. So you definitely know a few things here. But I will start from the beginning for the sake of people like Flynn, who told me that doesn't know much about the technique yet here. So he may be interested, and probably a few other people, to start from the beginning. And most people believe that Raman spectroscopy was discovered by Venkata Raman in India, and he was the only Indian, correct me if I'm wrong, who obtained a Nobel Prize for this work. However, Russian scientists, actually, there were almost simultaneously published a paper by Russian scientists in a different journal, and in Russia, therefore, it's called combination scattering spectroscopy, not Raman spectroscopy, because as in number of other discoveries, there are arguments who was really first discovered the technique. What was probably, of course, happening that absolutely independently, the scientists came to the same conclusion. An interesting factor, Venkata Raman published his finding in Nature, and Russian scientists published it in Annales de Physique, I believe, yes. So in a pretty good physics journal. Raman got a Nobel Prize. Russian scientists are pretty much known for their discovery in Russia. So this is kind of an anecdote showing sometimes how important it is to publish it in a more noticeable, high-profile journal, if you have certain results here. And the idea of the process is fairly simple. What you do, you take a laser, you eliminate your sample, and you have a detector, spectrometer, that collects a spectrum. Raman used sunlight as a light source and his eyes as a detector. Now we have more sophisticated equipment, and actually Raman spectroscopy became commonly used after discovery of lasers. When coherent laser radiation became available, and this is where technique became really popular. Here. What you collect is a spectrum that contains, of course, Rayleigh scattering, plus some much weaker peak, which are shifted in the wavelengths from Rayleigh line, which are called anti-Stokes or Stokes line, and we will talk about their origin later. So, where does Raman effect come from? What you see here is a simple diagram which all of you can probably read, and many of you, I believe, have seen in the past, for spectroscopic transition in diatomic molecule. Raman spectroscopy is combined in a group of vibrational spectroscopy with, for example, IR spectroscopy, which is an older, better known technique, particularly in chemistry. In case of IR spectroscopy, you have absorption of light. In Raman spectroscopy, you actually measure emission, and if you excite a molecule to certain higher energy state, and it goes back to exactly the same state, you get Rayleigh scattering. Rayleigh scattering was already mentioned in one of the lectures today. However, it can go from a ground state to a higher vibrational level. Basically, in this case, absorbing some energy and emitting a photon with a different wavelengths. And this is exactly what is called Stokes scattering. Of course, you may have molecules which are already at the higher vibrational states. So what will happen? They will go to a high level and then return to the ground state. In this case, some energy is released. You get a photon emitted with a somewhat higher energy. As a result, you get anti-Stokes scattering. Naturally, at least at room temperature, you usually have smaller number of molecules which are in a high excitation stage, in excited state. So anti-Stokes scattering is typically lower in intensity compared to Stokes scattering, as you could see in the previous slide. So for practical purposes, primarily, and I apologize for turning lights on. I just push the wrong button continuously. So if you see irritating blue or violet light, just let me know. Here. Of course, what I showed to you before was the case for molecular spectroscopy. In reality, in solid state, you have to deal with interaction of photons, radiation with phonons in the lattice. And I felt badly showing previous slides in the past until I saw Millie Dresselhaus, who is considered to be god in Raman spectroscopy of carbon material, actually explaining Raman spectroscopy completely on the example of molecular spectroscopy things here, without dealing with gamma point or Brillouin zone and more complex issues here. This is an example of gallium-arsenide here. So I'll skip this and move to the differences between Raman and IR. These techniques actually, particularly in organic chemistry, are very frequently used in parallel because they give complementary information. Raman spectroscopy involves emission of light, IR absorption. In Raman, scattering is due to distortion of electrons around a molecular bond and polarization of a molecule here. So, type of bonds that are easily polarized will give you signal, will give you peaks in Raman spectrum. In case of IR spectroscopy, change in dipole moment is involved here. So, some other functional groups, some other bonds will give you much better IR signature. For example, diamond will give you a strong Raman peak, but no IR peak, it won't absorb in IR at all. But if you, for example, are looking for carbonyl bonds, oxygen on the surface of carbon materials, then IR is your much better tool compared to Raman, where it's very, very easy because it's difficult to find this peak because the bonding will be very small here. But infrared spectroscopy is hardly used for analysis of carbon nanotubes because dark absorbing carbon nanotubes are very, very difficult to handle. In infrared spectrometer, it's primarily used to look for functional groups on the surface for functionalization of nanotubes, and it is still very, very tricky. However, Raman spectroscopy allows us to distinguish between all carbon structures. So everything is aside. If you need to do fingerprinting, identify carbons, whether it's graphite, diamond, amorphous carbon, diamond-like carbon, graphitic carbon, nanotubes, fullerene, you name it. Raman spectroscopy is the easiest and best way to distinguish it here. That's why Raman spectroscopy is so widely used for analysis of all carbon materials, including carbon nanotubes here. So, to finish with the difference of Raman spectroscopy, same molecules, the carbon dioxide in this case, can produce Raman and IR spectra, but those will be just different vibrational mode. Symmetric mode, no change in dipole moment. It will be IR inactive, but polarizability fluctuates, Raman active. In asymmetric mode, you will have change in dipole moment, you will get IR spectrum here. Now, I won't overload you with equations. You have seen enough equation in the previous lecture, but this one is important because one of the major or the major problem of Raman spectroscopy is lower intensity. Regular, in average, in a Raman effect, 1 photon per million will be inelastically scattered, producing Raman effect. What does it mean? That intensity is very, very low. Venkata-Raman had probably very good eyes that he was able to detect this type of changes. But in Raman spectroscopy technique, a lot of effort is directed towards increasing the intensity of the signal. And if you look at this equation, you will see all possible ways to increase the intensity. One is its proportional number of molecules. So, larger volume of material you have illuminated and scattering, high is your signal intensity. Seems to be simple. You get a larger sample, put it under a laser beam, you get high intensity. Doesn't really work well in many cases. In carbon nanotubes, dark absorbing material, light doesn't go very deep into the sample, so you deal with the surface. You cannot have it cubed by illuminating a larger area. You can have it at maximum squared, go into a larger surface area. But if you want to do analysis on a single carbon nanotube, you cannot increase its volume. You deal with what you have, right? So what else can you do? You can play with the frequency of light, bringing it and it's important because it's in power 4, especially if by changing the frequency you can also affect polarizability. If you get molecule stronger polarized, if you get a resonance, molecule in resonance, you can have a dramatic increase by several orders of magnitude in intensity. So, if you want to have Raman signal from a single 1 nanometer nanotube, you need to get right frequency, you need to bring it in resonance. This is your only chance to get sufficient intensity from a single tube here. But what you can also do, you can change electric field strengths. And this is what is done by using surface plasmons, by using surface enhanced Raman spectroscopy. And I will talk a little bit about later today. So there are several ways for you to increase intensity, and those are all important because if you don't do it, you frequently get very, very big spectra that cannot deliver much here. So what do we do in Raman spectroscopy? Something very simple. We take a difference, shift, what we call Raman shift between the frequency of the excitation wavelengths, this is usually our laser beam, and scattered light. And this shift, which is typically called Raman shift, will depend on the chemical structure of the molecule, basically on bonding. In this case, bonding in carbon nanotube between carbon atoms. And we already talked about the intensity of Stokes, anti-Stokes light, and as you could see from the previous equations, proportional number of molecules being excited here. Now, when I record the Raman spectrum, I can plot it in frequency or wavelengths or Raman shift. Tell me, why is Raman shift always, virtually always, used for plotting the data? What is the advantage to presenting this spectrum as something maybe a little bit unusual for some of you Raman shift? Why do we use Raman shift relative to the Rayleigh line, instead of just plotting frequency or wavelengths, as we do in a variety of other spectroscopies? It's a purely ideas. Well, there are some people who definitely know this, right? No, it's just a matter of convenience. Let me tell you. You can use a variety of excitation wavelengths. And if I use Raman shift, I can tabulate the data and tell Raman shift of diamond is at 1332 inverse centimeters. If I plot it as a frequency or wavelength, I will have tabulate data for every single excitation wavelength I use, what is just simply very inconvenient. That's why it's always used relative to the Rayleigh line, relative to excitation wavelength. Then whether I use green or blue or red laser, I will always have the same data, unless you have some other effects, and we will talk about it here. So low intensity is the main problem of Raman spectroscopy. Well, this wonderful technique has another major problem. 90% of materials in the real world fluoresce. And the intensity of fluorescence is usually much, much higher than intensity of Raman spectroscopy, just because the yield is much higher. So what happens? You get a fluorescent background covering your Raman spectrum. You all know that fluorescence is just an emission of photons by molecules when you excite it to a next electronic level. This is a problem for Raman spectroscopy. However, as we will talk later today, fluorescence of carbon nanotubes can also be used for identification of nanotubes. Moreover, this is the only way to really exactly and uniquely determine Hamada indices of carbon nanotubes. So, if you do Raman spectroscopy, this is a problem. If you use fluorescence spectroscopy, this is what you want to have, and this is what you want to use, particularly playing by comparing excitation and emission spectra, as I showed in the first slide, because there will be always some changes in energy due to losses in the transition. And I apologize, I have a blue and violet light again. What is also important? The strongest fluorescence is usually produced when you use somewhere yellow-orange light. So, no one uses, therefore, usually lasers in this wavelength. So, typically, most commonly used is a green laser or red lasers. For example, 514 argon-ion laser or 780 nanometer diode laser here. You can also go to UV, and this is where fluorescence usually is the weakest. So, just to give you an example, you can enhance significantly, because again, difference in frequency common power 4, your signal to noise ratio by changing the excitation wavelength. So this is also a reason why many laboratories have variety of excitation wavelengths. It's typically not enough to have a single laser unless you work with very specific material and you know this particular the best one. And also, some people use tunable lasers to obtain any wavelengths required. Now, nowadays, almost everyone uses Micro-Raman Spectroscopy. So what does it mean? Instead of just eliminating sample in a vial with a laser beam and collecting scattered light, people focus beam on a sample using a microscope. So virtually all spectrometer users, wide majority, are Micro-Raman spectrometers here, because you can do a lot of different tricks. You can collect light confocally from the sample from in-depth here. It's much easier to use because you see where you do the analysis. It's extremely important when you work with small samples such as carbon nanotube that you see at the limit of optical resolution, or frequently just as a dark line on the surface where you have no idea about the thickness, because definitely the diameter of the nanotube smaller than half lambda for the visible light wavelengths here. And you can also get high concentration of light even for very weak low power lasers in the spot when you do the analysis. And finally, you can also do mapping and imaging using microscope, which is useful for a variety of applications here. So, let's start with conventional, well-known carbon allotropes, diamond and graphite. Both of them will have a single line in the spectrum that is usually used for analysis. And in case of diamond, it's a triple degenerated phonon and 13-32 centimeters. And you can look at this from the standpoint that all bonds are equal in tetrahedral diamond or in hexagons of graphite where vibrations within the layer or diamond lattice produce you a single peak. It's all fairly simple, very simple spectra, very easy to analyze. And those are widely used. You see the peak for graphite is usually broader than for diamond because of disorder and stronger variations of lattice, some bending of graphene sheets, defects. Perfect diamond crystals give extremely narrow, 2 inverse centimeter of more narrow peak in Raman spectrum. Both techniques are widely used for both materials. For example, Raman spectroscopy is the only way, as far as I know, to distinguish artificially treated and colored diamonds from natural diamonds. So jewelers do a lot of Raman spectroscopy nowadays. First, this is a fast and easy way, so if anyone here has a sample for analysis, within a minute we can tell you whether this rock that you got from your boyfriend, your fiancé, is a real diamond or not, or if anything has been done to this crystal, for example, irradiation to improve its color. Here. Of course, it is also equally widely used for graphite. However, things become more complicated if you go to other structures. Here. Even graphitic material, if it has any defects, any edges of graphene planes which are within their laser beam, vibrations of edge atoms will give you additional peak which is called disorder-induced band and around 1350, and this is a double resonance peak which depends on the excitation wavelengths. So its intensity, its position will change as a function of excitation wavelengths. So it's not a true Raman band in this extent here. You can see carbene for sp2 bonding at around 2000 here, and you will see that for Fullerenes and nanotubes, additional bands appear, and we will talk in a moment about the reasons why. So, determining carbon allotropes is the first and very common application of carbon materials. But there are numerous applications for Raman spectroscopy in analysis of carbon nanotubes here. So first, just fingerprinting. I want to know whether the sample that I got from my collaborator contains single wall, double wall, multi-wall nanotubes. Is it really pure nanotube sample or sample with plenty of amorphous carbon? How ordered is this nanotube and so forth? I can determine purity. If I see amorphous carbon inside nanotubes and virtually all produced samples, as produced samples contain amorphous disordered carbon, I will have a strong D band. I can do stress-strain analysis. If I have carbon nanotubes and composites attached to the surfaces, I can determine what is the strain on the nanotubes. I can measure temperature. Raman spectrometer is a very expensive thermometer. You can take it this way. Not very accurate, but very expensive one. On the other hand, there is probably no better thermometer if you need to measure temperature of a single nanotube and you are at about 2,000 or 3,000 degrees C here. So there are some situations that this is the only way you do it here, and I apologize for a typo, it should be strokes, not strokes here. So as you can imagine, the intensity of anti-Stokes line increases with temperature. Relative to the intensity of Stokes line because you get a larger number of excited states. Or you can just look at the shift of the Stokes peaks in the spectra, which is induced by temperature, and measure temperature of the sample from it here. You can also measure orientations of carbon nanotubes. Very important. If, for example, we have aligned nanotubes on the surface or within a fiber, we want to know what is orientation, what is misorientation. You can use polarized Raman spectroscopy. Actually, laser beam is always polarized usually when you use it in spectrometer, but you need to have an analyzer that you can rotate and determine, get basically a whole picture for the tubes here, very widely used. You can measure diameters of single-wall carbon nanotubes, and I will tell you how to do it. Moreover, you can do it with a high accuracy compared to transmission electron microscope or atomic force microscope here. So this is the most accurate technique. You can also distinguish between metallic and semiconducting single-wall carbon nanotubes, at least whether your sample has primarily metallic or primarily semiconducting, or a mixture of both. You can find your tubes on the surface. If you see a glass slide and you cannot see anything with the naked eye, you may still get a good chance to see it with Raman mapping or imaging. Moreover, you can tell exactly where your nanotubes are, that you can do after that, for example, fabrication of a device around the tube here. And you can study in situ chemical reactions, functionalization of nanotubes, as you, for example, react carbon nanotubes with an environment, or do oxidation, purification of carbon nanotubes at high temperature here. And you can investigate interaction with the substrate, because the suspended single-wall nanotubes and single-wall nanotube on substrate will give you some different spectrum, because you affect vibrations of this tube, and you can also draw some conclusion. And you can even determine number of layers in graphene. And moreover, it's probably the only accurate way to determine number of layers of graphene here. So, in many cases, Raman spectroscopy is the only way to do the job. In some cases, it's just the fastest, easiest, highest resolution method. But it is still not perfect. I tell you a lot of great things about Raman spectroscopy, but keep in mind, you also will need other spectroscopic and microscopic techniques frequently to get supplementary information or answer a question you cannot answer by using Raman spectroscopy. Now, let's look more carefully at the spectra of other materials here. I won't talk much about Fullerenes. This is a single spectra I showed here. But look at wonderful spectra of graphite. You have the same carbon atoms. Moreover, most of rings are the same hexagonal rings. But instead of a single peak at 1580, I get a 1579 peak mixed, but I get very large number of other peaks. And if I blow it up, you will see that actual number is larger. And more complex Fullerenes here, for C70, the number of peaks will increase. Because in addition to vibrations in plane, you have numerous vibration modes possible now, and that's why you get such a complex pattern. But what you see here is actually a study that we conducted a number of years ago, studying decomposition of Fullerenes after hydrothermal treatment. You see at a certain moment, Fullerene peak disappear, and you get amorphous carbon, you get graphite peak, G band of graphite shifted here, and you get D band disorder-induced band of carbon. So you can do this type of studies here. Another example, before moving to nanotubes, is graphene. Graphene is a graphite, right? A single layer of graphite. So naturally it gives G band of graphite due to in-plane vibrations of carbon atoms in the lattice. But there is also a second order spectrum, which comes at about 2700. So this band has a doubled frequency of D band, double resonance, so 2D band considered here. What is interesting, again, Andrea Ferrari at Cambridge University has shown that position of this peak will change as a function of the number of layers. There will be a single peak for a single layer graphene, and it becomes more complex as number of layers increases until it becomes this type of a graphite-like band here. So this technique is currently widely used to measure number of layers in graphene when people produce single layer or multi-layer graphene. Moreover, this is also a good example to show an example of graphene, how chemistry changes will affect the Raman spectrum and how Raman spectroscopy can be used to monitor those. If you put graphene in hydrogen plasma, you can add hydrogen atom to graphene, making it hydrogenate, producing something which is called graphene. So this is hydrogenated layer of graphite. It's insulator, not a zero band gap semiconductor any longer. And what you see will happen, dramatic changes. You see D band appearing, you see some other weaker band appearing here. This is a reversible process. After annealing, hydrogen can be removed. So again, it can be monitored by using Raman spectroscopy. But also I wanted to attract your attention to this because it will be the same for nanotubes. Graphene on SiO2 and freestanding will give you somewhat different spectra here. So substrate has an effect here. Naturally, carbon nanotubes, very similar to Fullerenes, will have a variety of vibrational modes. Because in addition to plane vibrations, you have now bracing modes, because they can brace. Also, you have different modes within the layer of tubes, because you bend graphite sheet here. As a result, you end up with a much more complex spectrum, which has peak of graphitic peak of carbon, but now you see it is split into several peaks, and it contains lower wave number modes, which are called radial bracing modes because they result from bracing vibration of carbon nanotubes here. Both are very important. You can calculate those for various nanotubes. And the question I can ask you here, if you can calculate exactly Raman spectra for different kind of nanotubes, can you just use simply Raman spectroscopy like that to determine exactly how many indices of carbon nanotubes? Ideally, it would be possible. In practice, it is impossible. And the reason is very simple. The intensity of this peak is strongly dependent on the excitation wavelengths. Whatever wavelengths you use, some of them will be in resonance, some not. You will see some, you won't see others. And many of them are at very, very close position. So from Raman spectra, you can make guesses of what it can be, several options, but you can never tell for sure exactly what kind of nanotube you have here. But what is important for you to remember, and I think we will take a break after that because we have used 45 minutes here, that we have for carbon nanotube G band, which is typically split into several bands, similar to graphite, and we have radial bracing modes, and this is a Stokes and anti-Stokes spectrum, something that you can see and measure, and both are important for analysis, and I will explain you why after the break here. Any questions now? Is everything clear? Are you completely confused or just tired? Okay, we will leave the questions then. I say question.
CNTs with different diameters would have differently elongated between two bonds, and hence, in principle, the Raman shift would increase. The energy of the vibration energy of the bond will be different depending on the diameter of the CNT. Is it resolvable?
Yes, you will see it in a moment. Yeah. Well, in the beginning, after a break. So, how long is the break? 10 minutes, 15 minutes?
10 minutes.
10 minutes. So, in 10 minutes, I will show you how peak position depends on nanotube diameter, or how you can determine the diameter on from the peak position. Attention to the fact that when you read literature, you may find that people present Raman spectra in both ways. Traditionally spectroscopically, going from large wave numbers to smaller wave numbers, or, as it is becoming more and more common in Raman spectroscopy now, going from 0 to higher wave number showing Raman shift. And this may be confusing, and I already confused some of you, because in one of the very first slides I showed stock spectra being on the left side from Rayleigh line, and in this picture you have stocks, anti-stocks being on the left side and stocks on the right, so exactly the opposite. So this is the reality, so don't be confused when you read the literature. You can find people presenting data both ways. Okay, now let's think about G-band and Raman vibration of graphite here. So what is the difference between carbon nanotubes and graphite? In case of graphite, we had all atoms in one plane, and all the vibrations were in the same plane. What happens when we have carbon nanotube? We have a curved surface. So what does it mean? If you have bond in this direction or in this direction, you will see definitely certain changes in vibration frequency. As a result, you will see splitting of Raman band compared to highly oriented paralytic graphite, so it's pure graphite, or multi-wall nanotubes, which can be considered as graphite. You just have typically broadening of the peak here. In single wall, double wall tubes, you will see broader peaks. Moreover, metallic tubes will have a much stronger component at lower number, which is often marked G minus. It means lower frequency, lower wave number, or G plus, which is a higher wave number here. So this is convenient because you can differentiate between the samples containing primarily semiconducting and primarily metallic nanotubes by doing these things here, but clearly it makes the pattern more complicated here. Very similar way with radial brazing modes. You have a brazing of the tube, and radial brazing modes will depend on the tube diameter and strongly depend on the tube diameter. And it's inversely proportional, so the frequency will be inversely proportional by diameter. So you can calculate diameter of tubes by using Raman spectroscopy. However, again a disclaimer. You need to be careful because interaction between the tubes in the bundle, or if you have single tubes on the substrate, will also be able to shift the frequency to a certain extent. So you can make a mistake because this would be ideal for suspended nanotube, and if it's nanotube not suspended, what is the typical case, or in a bundle with other tubes, there may be changes up to 20 inverse centimeter in the tube position. And this is another reason why it becomes very difficult from this, even accuracy is relatively high, to exactly determine NM Hamada indices of the tube. So, and this is, for example, nanotube on a silicon wafer. You see a spectrum of silicon, and peaks coming here are peaks coming from different tubes. However, all peaks are widely used for analysis of tubes. So what we can do by looking at radial brazing modes and looking at G modes, we can determine diameter. We can determine purity by the presence and intensity of disorder-induced D-band, which comes from primarily amorphous carbon, but also from defects in nanotubes and, for example, etched open tips of carbon nanotubes. And we can determine whether those are metallic or semiconducting nanotubes from the intensity of this G minus mode. So those are at least three things we can do. With D-band, it's also necessary to watch that it will shift, and its intensity will depend on the excitation wavelength. Longer is the excitation wavelength, high intensity of the D-band, and also lower is the position. So if you take a deep UV laser, you won't see D-band at all, you won't excite it at all. And it will be shifted. So this is something just to keep in mind when doing analysis for the material. And also, since it's a resonance band, double resonance band, stocks and anti-stocks intensity will vary here. Now, what makes life of people doing analysis of nanotubes difficult on one hand, but may help in the other situation? Those are nanotubes that we produce, non-catalytic nanotubes in average double wall tubes, and you see radial Brezhnev mode region recorded using 3 different lasers: 514, 633, and 785 nanometers. And you will see completely different spectrum. While in a single, like a 2-micron spot that we use, we have thousands of nanotubes illuminated, probability that we get like a very, very different tubes in different parts of samples on a silicon carbide wafer is very low. But what happened? Resonantly, you enhance certain tubes, and as you change the wavelengths, you resonantly enhance tubes of different diameters. So, when I use green laser, I see some tubes. I switch to a red laser, and I see some other tubes. And it means that all these kind of tubes are present in my sample, and probably some others which I don't excite well enough with those lasers. So if you want to see, for example, changes, how after oxidation, elimination, small tubes, doing something else, diameter of the tube average changes, you certainly need to use the same excitation wavelengths here. On the other hand, when it's important, as we talked before, you can use resonance enhancement to determine virtually single nanotubes on the surface. But again, you may have 1,000 tubes scattered on a silicon wafer. And you do analysis in 1,000 points, and you find that 25 give you Raman spectrum. It doesn't mean that other tubes don't produce a Raman spectrum, but it means those are different tubes which are not resonantly, not in resonance when you use the specific wavelengths. So those are a couple of things to remember when you do analysis on carbon nanotubes. Now, I'm going to show you a couple of case studies, just examples of application of Raman spectroscopy to research on carbon nanotubes. And one of them is using in situ Raman spectroscopy for monitoring removal of amorphous carbon. And very similar way, you can also monitor removing in smaller tubes from carbon nanotube samples. All samples of nanotubes produced have usually plenty of amorphous carbon along with carbon nanotubes. So, in industry, it's mainly purified by acid oxidation, which is a nasty process, not environmentally friendly, slow, bad. And it was believed for a long time that oxidation in air, while cleaner, always burn nanotubes. It's impossible to find conditions here. One of my former PhD students showed that it's possible to do it when, instead of just doing oxidation, taking a sample out, studying it in the furnace, you exactly monitor the process by using Raman spectroscopy here. And what he did, he used a heated high temperature stage under Raman spectrometer and studied oxidation of nanotubes which were heated dynamically with continuous heating rate or statically step by step with a very high accuracy. You can go with 1 degree temperature and exactly see what is happening. And what you will find out that at a certain temperature, around 480, 490 degrees C, the band which comes from amorphous disordered carbon surrounding this nanotube, this double wall nanotube sample here, completely disappear. And you get tubes which have no amorphous carbon. And if you do it at the minimum temperature, just above 470 degrees C, you can remove completely amorphous carbon with no loss of carbon nanotubes at all. What will happen at higher temperature? You will not only remove amorphous carbon, but you also burn smallest diameter carbon nanotubes. It may be good, may be bad. If you want to produce sample which has only 5-6 nanometer largest tubes, it's very exciting. If you want to purify carbon nanotube sample with minimum loss of tubular material, it's not exciting because you will burn 99% of your material here. So all depends on your goals. But what is important that after this purification, you can get this wonderful sample with really no trace of D-band, no amorphous carbon. These tubes are very clean, as transmission electron microscopy shows. So this method works really nicely here. And of course, if you can use it to double-wall carbon nanotubes in a very similar manner, you can use it to single-wall carbon nanotubes. And this is another example. There is still some D-band remaining very big because it comes in this case from tips and defects in wall of carbon nanotube. But you can see air-oxidized samples have very nicely distinguished bands with a number of metallic nanotubes clearly increasing after the changes, and also RBM modes become much narrower. What does it mean in this case? We eliminate some carbon nanotubes of smaller diameter. Larger diameters tubes will have RBM modes at lower wave numbers here. And you can do similar things, of course, to multiple nanotubes. What is interesting? Initially, when you hit them, what is plotted here is a ratio of ID band to G band. So lower this ratio, less disordered carbon you have. So initially, you decrease it. You burn amorphous carbon from the surface. But if you go to high temperature, it starts strongly decreases, because what happens, you introduce oxygen atoms on the surface, producing defects on the surface of the nanotube. Again, both processes are important. You want to have clean tubes, but for many applications, particularly for dispersing carbon nanotubes, for mixing them, for making stable suspension of carbon nanotubes, it's necessary to have functional groups on the surface, otherwise they won't be dispersible in polar solvents such as water or alcohols here. So this is a way to control what is happening to carbon nanotubes by using Raman spectroscopy. And as I mentioned, you can do it on single wall, double wall, triple wall, multiple carbon nanotubes. It works nicely for all of them here. Another case study, measuring stresses in carbon nanotubes. When you apply stress to any material, you kind of stretch or compress the bonds. Naturally, you expect your vibrational frequency to shift. And what you can see here is a strain tensor for nanotube material. But what we need to know basically is that depending on the strain applied, again switching wrong things here, there will be some shift in the Raman peak position. And if you have a peak, for example, at no strain in a certain position, when you apply compressive strain, which way will it be moving? To larger or lower wave numbers? Compressive. Larger. So this one strain means compressive strain in this case here, assuming we go from 0 to high numbers. And naturally, there will be a shift in the opposite direction when you have tensile strain applied here. Actually, what will happen if instead of applying strain, I hit my sample? If I hit my sample, increase the temperature. Well, again, I have like an extension of the bond, so it's like equal to applying tensile stress. So it means that there will be a downshift of the peak if I measure temperature. So measuring this peak position, you can measure strains, or you can measure temperature if you hit the sample from shift peak. In the Raman spectrum, yes.
But like, if I'm not mistaken, like when you hit your samples, it could be like the shift could be not only due to the strain or stress, it could be due to chrono-chrono interactions and, for example, expansion of volume or something.
Sure. No, but I mean not the strength here. Basically, what you have elongation of the bond when you hit it here. So it's kind of similar to applying tensile stress. So usually this is because of this. And of course, more accurate way to compare with antistocks, but in many spectrometers you cannot record with the same intensity antistock spectra. So it's often convenient to monitor change in temperature just purely from the Stokes band shift.
So in case of nanotubes, it will be mainly because of the strain?
No, it is basically because of expansion, purely expansion. So basically elongation of the bond of the material. thermal expansion here. So what you can do in case of piezometry, what we studied here, we worked with colleagues from University of Pennsylvania, with Karen Biny and her group. They put carbon nanotubes in PMMA fibers. And the tubes are largely aligned along, along a 50 micron fiber. And we know that wherever we measure positions, we get very nice, very reproducible spectra, and we deconvolute the bands, looking at position of the most intense bands, G2 band here. What you also will see is that carbon nanotubes placed inside the polymer have somewhat slightly different spectra compared to free purified nanotubes, so there is certain effect of interactions with the matrix, which may suppress some bond vibration here. Now, what we did, we again under Raman spectrometer strained the fiber. We have a tensile stage when we apply stress, and we can stretch fiber under Raman spectrometer. And we can monitor how peak position changes as a function of applied strain here. So what we observe, we can measure stress or strain in the fiber. Basically, this is what is shown here is called stress-strain diagram for pure PMMA fiber, for PMMA fiber with single-wall carbon nanotubes, and we look at position of G-band of this nanotube, single-wall tubes. And what we see is that there is a significant shift to lower wave numbers up to a certain strain, which is thus 0.2%. And what happens after that? The dependence becomes much, much weaker after it becomes independent. What does it mean? That until this stress, we transfer load from polymer to carbon nanotubes. But above certain level, carbon nanotubes can be pulled out of the polymer matrix, and there is no interaction, no really strengthening any longer. And this is kind of an interesting result, because these polymers can deform to about 10-50%. And before, people couldn't understand why very little effect of carbon nanotube is seen. This experiment shows that only until very, very low strains, there is really a strong interaction between tubes and matrix. After that, tubes don't play any role. Moreover, what you will see is that, to confirm this, we can monitor change the position of the peak as we load and unload the tubes. And what will happen? If we load it below 0.2%, with unloading and loading part of the curve completely coincide. It means that we elastically strain nanotubes and let them relax. If we go to a higher load, 0.5% strain, high deformation, it doesn't come back. So deformation becomes irreversible. It means that we displace tubes from the position where they were initially. So it gives us opportunity to get insight into behavior of nanotubes in the composite that would be impossible to gain by other methods. And we can do it, of course, with a very high resolution, with, say, 1 micron or better spatial resolution, so we can see also, for example, changes in stresses within the volume of material. So there are this type of a very interesting, important thing for carbon nanotubes research that can be done using this method here. Now, switching the gear. So I hope it gave you some ideas of what can be done by Raman spectroscopy. A few more things about Raman spectroscopy before moving to other techniques. Still, while resonance helps us often, intensity maybe become not sufficient. So what can be used is technique which is called surface enhanced Raman spectroscopy. When we modify the electric field, actually enhance electric field by using metal nanoparticles. Gold and silver are the most widely used ones. While silver may provide high enhancement, it's less stable environment, so gold is probably the most common one used here. And signal enhancement up to 10 to the power 14 has been reported. You should take it with a grain of salt, because you never know whether it's really results of enhancement truly for molecule or high concentration of molecules in the field of a particle that you get here. But for practical purposes, 4 or 5 order of magnitude enhancement is common and very much achievable. So we can use it for two purposes. One, for example, you can look at very small number of certain molecules or functional groups on the surface of carbon nanotubes that you cannot detect otherwise. For example, in the beginning I mentioned one of the challenges people face is how to determine, for example, defects, oxygen, hydrogen, other atoms on the surface of carbon nanotubes. Raman spectroscopy can help. But what, for example, Elena is working on, she develops probes that are based on carbon nanotubes, contain cold particles on the surface, and can be used for probing the environment here. And there are several ways to conduct surface-enhanced Raman spectroscopy. Let me go back for just a second. Conventional, most common one is just using agglomerated particles, relying on hot spots between the particles, or using scratched, roughened surface, again getting source in certain occasions. The problem with those is that those are kind of a random enhancement. You enhance it in one point, less another point, you don't know exactly the level, it's very difficult to control. One way that industry is using it now, like Clarite produces substrates which are microfabricated. It's kind of a photonic crystal made in a metal surface. Why is it jumping ahead automatically here? And those give you, as I mentioned, around 10 to the 5 sensitivity enhancement compared to bulk Raman, and you get more reproducible pattern because you have reproducible particles here. So in general, for all this message, you can get label-free detection, but what we also want to have, we want to have probes which are very small, which can go anywhere, which are based on a single carbon nanotubes. For example, go into a cell, or be installed invisible probes to probe environment monitor, flow in water, environment in this room, and being able to detect just a few molecules, for example, toxins in water or in the room, or go and do study on single organelle in the cell. So what we wanted to do is to have a source probe which will be really small on a tip, which will allow us real-time monitoring, analysis, for example, in cell biochemistry. Elena will show a poster tomorrow where you can learn about the details of the message. But this is a result that she achieved initially in glass. What is important, she distributed gold particles in a kind of a uniform way and at the optimum distances that showed experimentally give the highest enhancement for the given wavelengths. As a result, we have very small fine probes with small tips about 100 to 100 nanometers that can do surface enhanced Raman. And what is important, the field enhancement occurs within 20-40 nanometer distance from the tip. So you actually improve your spectral resolution. You don't get Raman signal from entire area illuminated by the laser beam. You get Raman signal from a much, much smaller area. And you can, for example, clearly see differences for the cytoplasm and nucleus inside the cell here. Also, a similar principle used for the technique which is called tip-enhanced Raman spectroscopy. When people have a gold particle, silver particle on a tip of a small needle, for example, atomic force microscope tip or optical fiber, and they bring it to the surface, to the objects that they want to analyze, and then within, say, 40 nanometer, 50 nanometer area, there is an enhancement of signal. And this is another way to get Raman signal from a very small area with very good spectral resolution and strongly enhanced. And this method, for example, can be used to produce maps with nanotubes, seen not like an optical resolution line if the single nanotubes, but with a much higher, in this case, for example, 25, 35 nanometer positions accuracy, which is probably would be at least 20 times better that you can get with standard optical imaging. And this was done by Novotny group by pretty much scanning surface enhanced Raman tip over carbon nanotubes laying on the surface and eliminated from the bottom here. So this is type of a nice thing that can be done on nanotubes and using nanotubes with surface enhanced Raman spectroscopy. Good. Well, there are a few other things. Of course, you can do mapping by collecting spectra in different points, and then with the help of software, analyzing any peak position, doing stress analysis, doing other things. Or you can do also global Raman imaging when you select a certain narrow wave number band, for example, like a 10 or 20 wave numbers, and just on a CCD camera capture a picture wherever it gives this intensity. For example, again, if you look at carbon nanotubes dispersed on the surface or something like that. This is an example for diamond. I just didn't have a picture for carbon nanotubes here. Both have pros and cons. Global imaging is much faster, but you just get a single peak, so you cannot do much analysis on it. Mapping is slower, but you can analyze everything because in every point you have whole spectrum, entire spectrum captured. So you can do stress analysis, you can look first at peak of radial brazing modes, after that at G-band and anything else here. So those are useful things that can be done. And of course, you can do nicely images with cars if you have access to cars setup, what not everyone does here. And this is my last slide on Raman spectroscopy. 2 warnings. Carbon nanotubes are black. They absorb light very easily. There was a beautiful experiment shown by Adrian that you can take a regular camera with a flash, put carbon nanotube powder on the surface, take a picture, and carbon nanotube will self-ignite. Because they absorb light so quickly, so easily, and those are very thin tubes here, so you can raise the temperature very, very quickly. Of course, when you do Raman analysis on carbon nanotubes, and those of the powder have poor thermal contact between the single tubes, you can do exactly the same. White light you see here is not because white laser is used. As Mohan told us in the morning, whatever laser or whatever color you have, if temperature is high, it will look white. So in this case, you have probably about 2000 degrees C. We were able to go well above 3000 degrees C, evaporate carbon with a very low power diode laser very, very easily within tenths of a second that the laser pulse was applied here. And this is very important to understand. What you see here is a plot of G-band position as a function of temperature. You see, if you see shift from 1594, was for this particular sample tubes, to 1578, it means that you are already at 450 degrees C. Do you remember what I told you? That at this temperature you already start oxidizing amorphous carbon. If you are at 1565, you are at close to 1000 degrees C temperature. So it means you simply burn all the carbon that is in the sample. So if you apply high intensity laser beam, as I try to apply high intensity light to you, you can burn your sample before you even record your first spectrum. So you need to be really careful and check you don't hit your sample, because all results of your measurements can be affected by laser beam hitting. So to avoid this, people use sometimes cooling media. For example, water. And this is an example, it's actually for nanodiamond, not for carbon nanotube. But what is important is that water has also some weak but noticeable Raman signal, which almost exactly overlaps with G-band. It is somewhat high. It's basically OH vibrations, which are much stronger at around 3500, but weaker but noticeable around 1340, 1350 inverse centimeters. So again, they can affect your measurement of anything around G-band here. So there are quite a few errors you can make by using Raman spectroscopy. So if you want to do it well, you need to understand what you do. You need to be extremely careful. You need to check that you don't burn your sample, you don't hit your sample, that you don't shift your peak as you do study and measure spectra one after another for a long time. Only then you can get really useful scientific results here. Okay, now I have about 10 minutes left, and I will try within this 10 minutes to squeeze another 100 slides dedicated to other spectroscopy techniques here. Well, don't worry, it's probably more like a 10 slides or less, and I will be brief on those here. What is also important, there are other optical characterization techniques which are useful for a variety of applications, particularly for studying individual nanotubes. I already mentioned fluorescence, but also very simple Rayleigh light scattering can also provide useful information about carbon nanotubes. And both have been used extensively to analysis of single wall and double wall carbon nanotube samples. This is where those are useful. Well, we talked about nanotube electronic structure, and I don't remember if I mentioned yesterday this Van Hoff singularities for the transitions here, but what is important here? If you look at density of states of nanotubes, this is an example of a semiconducting tube, you can basically monitor optical transitions that occur in the nanotube and benefit from doing this here. And almost 10 years ago, exactly 10 years ago, actually 99, Catalura showed data calculated. Basically what he plotted are gap energies between this mirror image-like spikes in density of states like E1, R11, E22, E33, and other things here. For nanotubes with different diameters. And what appeared to be important, that for the same, say, wavelengths, for the same energy, you can see several different nanotubes given with different diameters, giving you basically peak fluorescence at the same energy. So, what is important therefore, that if you want to do analysis and really identify exactly the tube, you need to consider both excitation and emission wavelengths. Then you will be able to exactly pinpoint what you get. And this has been done later by Bruce Weissman's group at Rice University, who actually commercialized technique. You can buy fluorescence spectrometers for Raman nanotubes which can contain software. In this case, pretty much, every dot in this pattern, which is a plot of excitation wavelengths, emission wavelengths, correspond to a single kind of carbon nanotubes, and you can exactly assign Hamada indices to these specific nanotubes. So there is a way now to identify carbon nanotubes and tell exactly in the sample how many type of tubes you have, and whether your sample is strongly enriched with one type of nanotubes or contains a variety of nanotubes, that it can be done better than Raman spectroscopy here. So this is a nice way to do it. It's widely used now, and as I mentioned, even instruments have become available through Bruce Weissman's company here. There is another simple but useful technique, Rayleigh scattering. Rayleigh scattering intensity, as we already discussed, 1,000,000 times stronger compared to Raman scattering. So this is a good thing about it. You can use this very simple configuration, and pretty much you do dark field imaging or carbon nanotube which are suspended in a hole or lay on a substrate, and measure the intensity of Rayleigh scattering. What people did, they put single nanotubes grown between or positioned by dielectrophoresis between two electrodes, that you have a suspended nanotube, and this is a SEM image. You see this nanotubes bridges the gap between two edges here, and you can see scattering coming from a single nanotubes. This is a Columbia University group here. What is important? Different nanotubes will absorb light, scatter different wavelengths. This will be different from metallic semiconducting tubes. These sets of peak look similar, but you will see that positions of the peak are different here. And by using this technique, a couple of interesting things were shown. That the spectra depends really on chirality of the nanotubes, and you can again assign them to certain nanotubes. You can see groups of tubes with similar properties give you a similar spectrum. And finally, a nice experiment that was shown, was done in a series of samples to show that nanotubes are typically, if you look at the along the tube go and measure the spectrum here, that spectra at the top or bottom, for example, will ideally completely coincide. What does it mean? That you have no correlated change along tube. And keep in mind, if this is a tube is 40 micron in length, and say, well, let's take for simplicity 1 nanometer in diameter here, it's a 40,000 aspect ratio. So this is a very, very, very long cable. And as it grows, there is no change in the correlacy of the tube. However, it was also shown that there may be some changes. Moreover, it was recently shown that, for example, by irradiating tube it's possible to introduce defects, introduce changes. For example, changing metallic to semiconducting behavior of carbon nanotubes by modifying, by oxidizing tubes. So it gives opportunity to again study changes in the electronic structure and properties of carbon nanotubes here. So these techniques are definitely useful, and Rayleigh scattering of individual nanotubes is used pretty much for getting signatures of electronic structure of the tubes, studying transitions and changes along the nanotube direction. Also on Y-shaped nanotubes studies have been done using this technique I've seen. Study interaction of tube with the environment, again important for sensor application of chemical modification, and probing mechanical displacement. Very similar way you can apply stresses and see what happens here. And of course, it can be combined with diffraction studies or electric transport, basically electrical properties, conductivity measurements in the same setup, what becomes more and more common. So there are a lot of interesting things that can be done using optical spectroscopy techniques on carbon nanotubes. And what is also interesting is that virtually probably 90% of data I showed to you were generated within the last decade, many of them within last year or two. So this is an area which is not like established, set, and pretty much already going flat here. This is the area where enormous growth is happening. People are looking for answers to many open questions still. People are trying to develop new techniques, particularly for in situ study, for monitoring what is going on with nanotubes, graphene-related materials. And again, there is a huge room for further improvements, and this is a nice research area for those of you who are interested in the topic. Thank you very much for your attention. Do you still have any energy left for questions? Yes, please.
How can I suspend a single nanotube?
How you can span or suspend? There are two ways to do it. One way is, and this was done particularly by this Columbia group, what is done is growing it right at the site. So basically you have like a substrate with microfabricated substrate, you deposit particle of catalyst on edges. And of course, this three-dimensional, they deposit many particles of catalyst and do chemical vapor deposition. One long tube grows, and at least some of them will drop and span the bridge, forming pretty much a bridge to the other side. So they were looking at this film. So this is one way to do it here. Another way of doing it, using dielectrophoresis. If you put two electrodes on the surface, you can get nanotube from a droplet with a solution, which will go and lay exactly with the electrode, short circuiting, stopping circuit. It's a very common technique for placing tubes to the location. So people use both methods for placing tubes between two electrodes and suspending the tubes. And this can be done either on elevated contacts, or area underneath can be after that dissolved, etched, removed. And tubes can also be fixed by, for example, depositing metal on the surface and focused time demolas for here.
Another question is, how can you suspend graphene? Graphene is not
Graphene is suspended actually kind of a similar way. It's not grown, but what is usually done is graphene is purely from a solution, usually, deposited by filtering on small gaps. And as it happens, it just sits somewhere, comes from the solution, deposits in the gap, and what is done, you have like a network or number of lines of electric contact growing here. And you have low concentration of graphene. Some flakes will deposit in the way that they will lay exactly between two electrodes here. And van der Waals forces will keep it from sagging completely.
Are there some tool of refinement of structure, Raman spectra, equal to rhythm refinement and excitation?
Not really. There is nothing that would be like equal to Rietveld requirement in XRT. Of course, what people do, if you know extensipated peak shape, usually people use Lorentzian or a mixture of Lorentzian and Gaussian band for D band here to fit the peak. So what you usually do, you just do peak fitting, and of course if you have some, say for nanotube theoretical calculation where you know where peak position should be, it is fine, it helps you to place your peak correctly. If you just get the best fit, there may be more than one solution.